Two questions for homework last night, page 186, questions 1 and 2. We want to look at both of these this morning. First of all, question number 1, where it says calculate the coefficient of static friction. So if it says static friction, it's not moving, right? We know this thing is at rest. Otherwise, we wouldn't be dealing with static friction. We'd be dealing with kinetic friction. If the toboggan in example 3.18 is 20 kilograms, and it's on a 30-degree incline at the bottom of the hill. The first thing we got to do, first thing we always do in a question like this is draw a free body diagram. The free body diagram shows all of the forces acting on the object. We know there's at least two forces acting on this object. One of them, Hayden, what's one of those forces? Gravity, and it acts straight down. Of course, that force of gravity is equal to m times g, 20 times 9.81. What's the other force that we know is going to act on this every single time? Rutger. Good. The normal force that acts perpendicular to the surface. Now, we know, we've seen this enough times now, we know this red line that is the sum of those forces, the combined normal force and force of gravity, the force that we call the force of the hill, that brings it down the hill here, we know that that force has got to be drawn parallel to the hill itself. In other words, the normal force and the force of the hill have to be the perpendicular forces. Make sure you get that drawn correctly, because that's the way that you ensure you use the right trig function when you're analyzing this. Now, we also know in this case that there's another force that acts. This doesn't always act, but it does here. What's the other force that acts in this case? What's the other force that acts in this case? Static friction. And which way does static friction get act, Krista? Up the hill or down the hill? Up the hill, good. Static friction has got to act up the hill because, of course, if the hill force is bringing it down, then static friction has to counter that, has to balance that. We know that, in fact, if we're talking about static friction and it's not moving, then we know that force of static friction is going to be equal to the force of the hill. So we'll draw it the same length. If it was bigger, it would go up the hill. If it was smaller, then it would go down the hill. Okay, so what do we do now? Let's label that angle. What's the value of that angle? How'd you know that so quickly? Okay, you're right, it's perfectly perpendicular to the hill, which is at 30 degrees. In the end, that angle down here at the bottom of the hill is always going to be the same as that angle between the force of gravity and the normal force. Always, no exceptions to that. So you can just write that down. Now what? We want to find the coefficient of friction here, right? We did a question like this yesterday, one or two questions like this yesterday. And you know, when you look at them for the first time, they look challenging. It looks hard. What do we do with this? Where do we go next? Just do things. Get things. You're not sure what to do next. Just get things. Okay, and something will fall into place eventually. Okay, do we know how to get something here? Okay, not necessarily the coefficient of friction. Don't panic about that yet. But is there something here that we know how to solve for? Anything. Okay, anything that might help me down the road here. Josh? We can find the force of the hill, yeah? So let's do that, okay? That's probably going to help me, right? Odds are we're going to need to do that, so let's do it. Let's say sine 30 degrees is equal to the opposite side of that triangle right here, which is the force of the hill, over the hypotenuse, which is gravity, 20 times 9.81. When we solve for the force of the hill here, it ends up being equal to 98.1 newtons. Okay, so that's FH. Good. That's one thing that we were able to find. Is there anything else that we're able to find? Again, we're not sure what to do with this exactly. We're not sure how to find the coefficient of friction. So let's just get something, anything that we're able to find here. Is there anything else here? Let's say, Laura, is there anything else that we know how to find here? Yes, we can find the normal force. It's the adjacent side of the triangle, right? So we're going to use the cosine function there. Cosine 30 degrees is equal to the normal force over the force of gravity. Am I doing this because I know this is going to lead me to the right answer? No. I'm doing this because I'm not sure what else to do, and I can do it, so I might as well try something. What's 20 times 9.1 times cos 30 degrees? What is it, 169? So now we have the normal force, 169.914 newtons. Okay, at this point, something might kind of jump out at you. It might not. Okay, at this point, we kind of have to make a leap if it doesn't jump out at you. We're going to say the force of static friction, the max force of static friction, which is really the one that we're dealing with here, is equal to mu times the normal force. Now, we know what the normal force is. It's 169.914 newtons. We also know what the max force of static friction is here. What is it? Travis? 98.1 newtons. We calculated the force of the hill, but we said when we drew the diagram that the force of the hill had to be the same as the force of static friction. So, let's rearrange this equation. And divide those two numbers, and we'll get the coefficient of friction. FFS is 98.1 newtons, and FN is 169.914. When we divide those two numbers, we should get 0.58. The units cancel, so that's my final answer, 0.58. How many people got that? Good. Good. That's a tricky question. That's a good question, but it's a tricky question. Okay, let's take a look at number 2. This one says an 80-kilogram skier on a slushy surface starts moving down a hill, forming at an angle of at least 25 degrees of the horizontal. What's the coefficient of static friction, and what's the max force of static friction on the skier? Let's draw the picture. We have an 80-kilogram skier. I'm just going to draw it as a box here, just because, whatever, it's easier. At 25 degrees, the skier starts moving down the hill. What do we do with it? Well, do what we always do. Draw the free body diagram. We got gravity acting down. As Hayden said in the last one, it's 80 times 9.81 this time. As Rutgers said in the last one, we have a normal force acting perpendicular. Call that Fn. We got to combine those to give me my red force. We're going to call that the force of the hill, which is always at 90 degrees to the normal force and is always parallel to the hill. So there's Fh. Any other forces acting? We're going to have friction, right? We're going to have friction. And that frictional force is going to act up the hill. And it's going to act up the hill with the same value as the force of the hill. It's got to be the same value because that's the angle at which it begins to move. That's the angle at which the force of friction actually becomes slightly less than the force of the hill, but minuscule amount, right? The force of the hill just starts beating the max force of static friction. So we're going to say that they're equal. Therefore, we're going to draw them the same length. And then we're going to go to work at analyzing this. Okay, we can find once again the force of the hill. I'm going to say sine 25 degrees is equal to FH, the opposite side over the hypotenuse, 80 times 9.81. Who's got a value for that, please? Josh? 3.3 times 10 to the 2 newtons. Thank you. Now we're going to find the normal force, because again, we're not sure what to do here right now, so let's get something. The normal force is out there. Let's get it. Cosine, because we're looking for the adjacent side, is equal to the normal force over the force of gravity. What's the normal force equal there? Do you have the value? You're right. 711.27. So what is the unrounded number there for the force of the hill? 331.691. Thank you. You're right. Don't round until the end of the question. You're right. Okay, so we got that. We got the force of the hill. We got the normal force. What are we going to do with that? Yeah. In the end here, right now, we can answer question B, right? What's the maximum force of static friction on the skier? Well, it's going to be the same as the force of the hill. Right? We've already done D. We've got the force of the hill. We've got the answer to question B, 3.3 times 10 to the 2. Now we want to find the coefficient of friction. Let's do the same thing we did in the last question. Mu is equal to FFS over Fn, which comes from that static friction equation. Okay, it's 331 over 0.711, which gives us 0.47. How many people got that one? Okay, good. Good. You guys are pretty good at this, I think. Yep, question? All right, I think what I want to do right now is give you a chance to put all this stuff together here. Yeah, we've done over the last few days a number of different kinds of problems involving multiple forces. Everything from those elevator problems, right, where you had the force of gravity and the normal force acting, and we wanted to find the apparent weight and the actual weight and the tension and all that stuff, to pulley problems, where we were trying to find the acceleration usually of a system given a couple pulleys, to these inclined plane or these hill problems. Okay, they're all fundamentally the same, but there's small differences in each one. I think what I'm going to do right now is give you a worksheet that's going to have questions from all of those things, okay, from elevator problems to pulley problems to inclined plane problems. And that's what we're going to do today, is work on those questions, okay? It's a good opportunity for us to focus on the ones that we're having trouble with, and it's a good opportunity for you to ask me questions as you have an opportunity to work. All right, so I'm going to hand them out, ask you to take one hand on to the next person, and then you can get to work on it.